Okay, let's go ahead and get started. I hope that everybody got my email about the issue with Android version of Cam Scanner. I'll let you know when they have a solution for that. In the meantime, it's okay for you to submit JPEGs if you were an Android user and don't want to figure out some other solution. Homework 2 is available now. Let me show you. That's just on MU Online in the same spot that Homework 1 was available. So all you have to do is click on the link and you'll see the new problems. There's 8 of them. I'm going to post a solution to Homework 1 later today. That'll be on MU Online, and so that you can look and see if you got the right answer for your homework. I anticipate that this semester the grading will take less than a week generally, so you'll have your scores and then you'll have the homework solutions posted if you want to get into the details of maybe where you've missed points or anything like that. All right, so that is the homework. If you look at the course schedule and are keeping track of various things, then you maybe saw that we're going to have a quiz next Thursday. And quiz are relatively minor graded events. I mean, they don't count for nearly as much as exams. The purpose of them is just to be kind of an intermediate spot check to ensure that your comprehension is where it needs to be, because it's a lot better to figure it out for like a 2% quiz than a 25% exam. And just to give you the feel for what the formatting of the quizzes and exams may look like, I'm intending to post a sample exam online from a previous semester. I'll put that on this afternoon so that you can go to MU Online and see what an exam a few semesters ago looked like. And sometimes you need to get the hang of not only the material but how the instructor asks questions. And so giving you that sample exam in advance will maybe be a chance for you to practice understanding how I ask things. Okay, so those are the announcements. Any questions about those?
Sorry. Quizzes. Will we be able to have a formula sheet or not?
No.
Okay.
But you should bring a calculator, because you're not allowed to use your mobile phone during a quiz or exam. Actually, you're not allowed to use your mobile phone at all, but especially not during a quiz or an exam. All right? Are there other questions? Okay. We've got 2 things that we're going to talk about today: vapor pressure and a first lecture on hydrostatics. As a reminder, the notes are available online if you choose to follow along with them as we do through the lecture. And of course, you've paid a little bit of money to rent or buy the textbook, and I'd encourage you to make a habit of reviewing the material in the textbook that relates to the lecture. It's just another point of view, another way of explaining the things that we're going to be talking about, and it's pretty uncommon for someone to understand new material the very first time that they're exposed to it. I think more typically the average is you have to hear something and think about it 7 or 8 times before you really absorb it and make it your own. So I'd encourage you to use your textbook as a resource for kind of refreshing your understanding of the material after the lecture. Okay. So what we're looking at here is boiling water. And you can tell, what are the clues here if you're doing the image analysis? The blue flame underneath, the rippling and the turbulence of the water, the steam and the condensation on the glass above the water. So there are a couple of different ways to get water to boil, and this is just the most common of the ways, is to heat it up. And when you heat water, what you're doing is you're changing something, one of its properties that's known as vapor pressure. At sea level, you have to heat water to a temperature of 100 degrees Celsius before it will begin to boil. And what you're doing when you're heating it is you're adding kinetic energy to the water molecules. And when they have enough kinetic energy, what they're able to do is they're able to break free from the liquid phase and go into the vapor phase. Even at lower temperatures, water will evaporate slowly, But when you elevate the water temperature above to the boiling point, then a much greater fraction of the water is going to be leaving and at a much higher rate. The interesting thing is that at higher elevations, you're able to boil water at lower temperatures. So for instance, on Mount Everest, if they make a cup of tea, that tea is only going to be 69 degrees Celsius because you're not able to heat the water any higher than that. If you add more and more energy to the water, it's just going to boil faster, but it's not going to increase the temperature of the water above 69 degrees Celsius because that's the vapor pressure of water at the elevation at the top of Mount Everest. So just to define some terms, vapor pressure is the pressure at which a liquid will boil. And it's dependent on temperature. And so when you elevate the temperature of water, you're increasing the vapor pressure. And here's a table of the vapor pressure of water as a function of temperature. And water even has a vapor pressure when it's frozen, interestingly enough. The process of a solid going to a gas is called sublimation. And it happens very, very slowly, but water will evaporate from solid ice into the atmosphere. If we're going to graph the vapor pressure of water, what you can see is that as you increase the temperature, the vapor pressure starts to go up a lot. And so water evaporates much more quickly at elevated temperatures than it does at reduced temperatures. At 100 degrees Celsius, water will begin to boil. And you can get water above 100 degrees Celsius if you confine it like in a pipe. You know, if it doesn't have the ability to evaporate, then you can have so-called superheated steam or water that's above 100 degrees Celsius. But we have this interesting case where you can boil water at lower temperatures if the pressure is lower than atmospheric. So let's take a look at this video just to illustrate the effect of boiling water at a reduced temperature. The idea is he was talking about all the heat that was being added was being removed at a rate faster because of the evaporation. The heat that was being added was removed faster than the water could increase its temperature. So all of the energy was being consumed by the boiling. So in more practical terms, you're not going to come across the case where you've got irons and pasta. Like the more common case for vapor pressure to be important is water flowing through pipes because it causes an effect called cavitation that we're going to talk about today. If you want to look up the vapor pressure of water, table A5 has that information at a variety of different temperatures. And the vapor pressure, you notice, increases till we get to 100 degrees Celsius. And at 100 degrees Celsius, water has the same pressure as atmospheric at sea level. As a practical application of vapor pressure and this effect called cavitation, an interesting case study is for a dam in Russia a few years ago. It's a hydropower dam. You notice it's a pretty large dam. It's got these big pipes going down the side of the dam. They're called penstocks. That feeds into a hall that has turbines and generators. And here's a picture, a before picture. Is that ominous? This is before. What happened was, well, just to give you a little bit more about the layout, buried in the floor of this hall are a series of turbines that the water flows through. And as you'll learn later in the semester, when you have elevated water that's flowing downward, you can generate quite a lot of electricity depending on the elevation difference between the upper reservoir that it's coming from and the lower reservoir that it's going to. And so they harness that potential energy and turn it into electricity. But the problem is that when you have a really high elevation difference, that the water velocity can get quite large. And I mean, it's to your benefit. If you're generating electricity, you want to have as much flow as possible to maximize the electricity that's being generated. But when you have high velocity water, the pressure decreases due to the Bernoulli effect that we'll talk about in chapter 4. So in this case, they had very fast moving water that caused a low pressure in those pipes. And the pressure in those pipes got so low that little air bubbles, excuse me, they're not air bubbles, they're water vapor bubbles. The water inside of this pipe, the pressure was so low that actually the surrounding pressure fell below the vapor pressure. So let's say if it was 15 degrees Celsius water, the pressure in the pipe fell below 1700 pascals, and then tiny little vapor bubbles started to form. And those vapor bubbles, when they collapse, they can send a shock wave through the water that has the capacity of eroding the pipe and causing damage to the material. If there's pitting of the spinning turbines, then it can cause an imbalanced turbine that can catastrophically kind of oscillate and gets worse over time. And you can see that we're looking at the same place. You look at the ceiling with the textured beams and everything. You can see these tanks on the side, and so it's a similar view. But what happened was that the cavitation caused damage to the penstocks and to one of the turbines, and eventually there was a catastrophic, almost an explosion at the plant, and so it was out of commission for quite a long time, and they determined that the issue was cavitation. We'll talk more about cavitation in chapter 7 of the book when we start to get into the energy equation and more design-related issues having to do with pumps. But for now, the effect that you need to keep in mind is just that if the surrounding pressure falls below the vapor pressure of the liquid, then those little bubbles will start to form. It's essentially that boiling occurs inside of the pipe. And boiling inside of the pipe is bad because those little vapor bubbles, they're tiny, but later on they'll collapse when they get into a higher pressure zone. And as they collapse, it occurs very rapidly, and it sends that high energy shock wave, and it will cause damage to the pipe or to impellers of pumps and turbines. Okay, we've talked about pressure before, and you've seen the trick question that at the bottom of a reservoir, it doesn't matter if it's a narrow reservoir or a wide reservoir, that the pressure is the same and it acts equally in all directions. We're going to continue that discussion today with an approach on how you can calculate the magnitude of pressure at a certain depth. Here's the hydrostatic equation, and what it says is that pressure changes as a function of depth. And it's an opposite relationship, so that if you go down through a liquid, meaning that the Z is decreasing, the pressure is increasing. And it does that at the rate of gamma. And so who recalls what is gamma for water? What's the value of the unit weight of water? Right, 62.4 pounds per cubic foot. And in SI units, 9810 newtons per meter cubed. That'll be burned in your memory by the end of the semester for sure. So what this is saying is that if you go down 1 meter of depth, the pressure is going to increase by 9810 newtons per meter squared. And so this is a rate. The rate of pressure increase is equal to gamma. That's the hydrostatic equation. Now, a datum can be at the bottom of a tank. It could be at the liquid surface. The elevation datum can be anywhere. That doesn't affect the general trend that as you go up through a liquid, meaning that the Z is increasing, then the pressure decreases. But if the Z is decreasing, the pressure goes up. And so looking at the units, if we know that gamma is 9810 newtons per meter cubed, and I said if you go down 1 meter, then the pressure increase will be 9810 newtons per meter squared. And so what we do is we multiply the depth times the unit weight, and that gives us the change in pressure. So in other words, if we rearrange this equation, if we have the dz and multiply it by the gamma, then it will tell us the dp. The change in pressure is the unit weight multiplied by the dz. And just again, the negative sign there is to remind us that the pressure increases as the elevation decreases. That's the general relationship, and there are a few things that we have to keep in mind when we do problems related to going down into a fluid, pressure variation type problems. We'll assume that in fluids the density and specific weight is uniform, and that's a pretty good assumption for liquids. It's a less good assumption for gases, atmospheric gases, because if you go up in the atmosphere, the density of air is decreasing. As you get higher up, the pressure goes down, and so does the density of the gas because it's expanded. But if we're only going up or down a relatively small number of meters, then it's still okay for us to assume this constant density even for gases. But for liquids it's fine, because liquids, as long as the constant temperature applies, the liquids have the same density as you go down through the fluid. Now, this hydrostatic equation, if we integrate it, there is a relationship that we call piezometric pressure. And that is, the piezometric pressure has two terms. It's the pressure term and then this elevation head term. And what it says is that in a tank of water, if you go from place to place in a tank, that there won't be a change in the piezometric pressure if this water isn't moving. If it's just static water, meaning stationary water, any two locations you can have loss of elevation but an increase in pressure, and so between 2 points the piezometric pressure would be the same. And another way of thinking of this is if you multiply each of the terms by gamma, then that's piezometric head rather than piezometric pressure. And so the same thing is true, that in a tank of water between 2 points where the water isn't moving, you'll have a constant sum of the elevation and the pressure head. But those two things are interchangeable. Like at 1, you may have less elevation, 1 is higher, so it'll have more elevation but less pressure. And then when you're moving between 1 and 2, the pressure increased but the elevation decreased. So the hydrostatic equation, sometimes rather than just thinking of it as this change equation, what we sometimes do is we identify points in a liquid where we are able to make a measurement, and then another point where we're interested in calculating what the pressure might be. So if we know the pressure at 1 and we know its elevation, then we can predict what the pressure or elevation at 2 is going to be if we know the other of the terms. And so if we know the pressure, then we can calculate the elevation. If we know the elevation at location 2, we can calculate the pressure. And we're going to get some example experience with that today. Let's just do that with this tank. Let's say that at 1, we know the elevation is 34 meters above some datum, and the measured gauge pressure is 66,000 pascals. What does gauge pressure mean?
How much pressure is above atmospheric pressure?
That's right. So gauge pressure is using atmospheric as the baseline. And so we're assuming that the pressure of the air that's above this tank, we're calling that 0. Now we know that the air doesn't actually have 0 pressure, it's just that we're using that as our starting point for measuring any additional pressure beyond that. So what we want to do is we want to find the absolute pressure at 2. So this is kind of a, first the gauge pressure, then the absolute pressure at 2. And so here, using this hydrostatic equation, We know the pressure at 1. We know the elevation at 1. Since this is water, and they don't specify the temperature, then we'll just use the standard unit weight of water, 9810 newtons per meter cubed. And what I'd like you to do is calculate the absolute and gauge pressure at 2. Did everybody bring their calculators today? Good. Very good. You're prepared. All right.
What number did you get for that?
Okay, so here is the solution for part A. We're just using the hydrostatic equation to talk about a pressure change through a static fluid. That equation doesn't apply if the water is moving. At least it doesn't apply very well. It can still be used, but then there's going to be some errors, and we'll talk more about that later. But for now, if we just rearrange to solve for P2, then the gauge pressure, assuming that P1 was given in terms of gauge, that's going to give us P2 in gauge. It should be 144 kilopascals, or 144,480 newtons per meter squared. Either one's okay. Now, as I've written on the board, the way that you can convert between gauge pressure and absolute is if you're given the gauge pressure and you want to know the absolute pressure, you have to add on the atmospheric pressure that was ignored the first time around when you had the gauge measurement. So P absolute is P gauge plus the atmospheric pressure. So for this one, our gauge pressure is 144,480. Atmospheric is 101,325, and so the sum of those two gives us an absolute pressure at that location 2 is going to be 245,805 pascals. All right, so does this make sense? Hydrostatic equation. Now this is the full hydrostatic equation. Sometimes, though, it's just as easy to use an abbreviated version of it that keeps track of the change in pressure due to a change in depth. And so this is kind of similar back again to that idea of the dP and the dz. But here, instead of measuring the change above the datum, the delta H that this talks about is just some change in depth, whether it's up or down. And so the way that we'd use it, for instance, if at the bottom of the ocean, like the real bottom of the ocean, I think that location is called Challenger Deep. It's in the Mariana Trench. And if we're using the unit weight of seawater, so the gamma of seawater is a little bit higher than the gamma of ordinary water because the salt adds to the density, then the pressure change, the delta P from the surface of the ocean, where we're assuming that the air is touching the water, and so the pressure right here at the interface of the air and the water, that pressure is 0 gauge. Usually we're going to be doing gauge pressure. I'll stop specifying between the two, and it will be the exception that we have absolute pressure. Usually the only time that we'll use those absolute pressures is for gas law type problems. But if we want to know, if we go down 10,911 meters, what is the pressure at the bottom of the Mariana Trench? The delta P is the delta H times gamma. So the delta H would be 10,911 meters. The unit weight of seawater, 10,100 newtons per meter squared. And can someone with a calculator multiply those two together? I'm sure I've got it here somewhere, but maybe it's just easier for you to calculate it fresh than me to find it in my notes.
Here. It's a big number. Right?
Okay, just start telling me numbers.
110211100.
All right, so now let's put those commas in there. So it's 110 megapascals. So if we have newtons per, oh, I'm sorry, this was newtons per meter cubed for the unit weight of seawater. So that gives us newtons per meter squared, and that is 110 megapascals, so MPa. So there's a lot of pressure down there at the bottom of the ocean. Okay, so that's the abbreviated version of the hydrostatic equation. Now the interesting thing is, what if you have different liquids? Like if you've got an oil floating on top of a water, how do things work then? Well, the general trend is that pressure is additive. So if you have oil with a specific gravity of 0.75, meaning that its density is 750 kilograms per cubic meter, if we have a layer of it that's 1.1 meters thick, and then this tank, the total liquid level from the top of the air-oil interface to the bottom of the tank, that distance is 4 meters. So we've got a 1.1 meter layer of oil. The total liquid level is 4. What is the gauge pressure at the bottom of the tank? So the way that we'd solve a problem like this is we start at the place where you know the pressure. And we know the pressure at the interface of the air and the oil. So the pressure here is 0. Apply this equation through the first layer and find the pressure at the interface of the oil and the water. You can't go in a single step from the top to the bottom because there's two different gammas. That's why you can't just do it in a single step. You have to break the problem up into as many steps as there are different liquids. So here, if you want to find the pressure at the bottom, you'd first find the pressure at the meeting point of the oil and the water, and then in the second step, the pressure change would be from the oil-water interface down to the bottom of the tank. So I'd like you to try that out. I'd like you to see if you can find what is the pressure at the bottom of that tank of oil and water. And we're doing this at gauge, which means we assume 0 pressure in the air. Okay, so what we need to do first of all is find out the depth of the water inside of there. That's a trick sometimes I get people on, is by only giving the dimensions of 4 and 1.1. You know, you got to make sure you got the right depth distance that you're using. All right, so we're going to do it in steps. First of all, at the interface of the air and the oil, because we're talking about gauge pressures, P1 is 0. And then P2 is going to be whatever the pressure was at 1 plus the delta, so plus the change. And so P2 is 0 plus 1.1 meters of oil. And up here in the preliminaries, I had calculated the unit weight of the oil with the given specific gravity. And so the specific gravity, you can think of it as a percentage relative to water as the reference. And so 0.75 means that the unit weight of oil is going to be 75% of the unit weight of water. So we calculate the unit weight of oil and get 7357.5 newtons per meter cubed, and then that's the one that we put in here for the 1.1 meter layer of it. So at the interface of the oil and the water, the liquid pressure is 8093 newtons per meter squared. Any questions so far? So we just apply the same process through as many layers as there are. If it was oil, water, and mercury, then we'd have to break it up into an additional step. But here, to get down to the bottom of the tank, we now have to say that P3 is going to be whatever the pressure was at 2 plus the change. So we already knew the pressure at the interface of the oil and the water. Now if we're going downward an additional 2.9 meters through water, the pressure is increasing at a rate of 9810 pascals per meter of depth. So in this case we've got 2.9 meters of depth. And this is a habit you'll see on some of the solutions that I show you, this like bracket and the intermediate calculations. I got in the habit of triple checking my calculations when I was in your shoes, because when I took exams we had unlimited time. Can you believe that? Wouldn't that be nice to have unlimited time for exams? Because the instructors, what they did is they put the test in a testing center and you could go take it anytime you wanted within like a window of time. And so with unlimited time I'd triple, quadruple check my calculations sometimes. And so I just found it was easier to check my answers if I kind of wrote some of the intermediate calculations on the page. And so you'll sometimes see me do that. And I don't think it's a bad habit for you to maybe consider, even if you don't have unlimited time on exams. You know, it still pays to double check now and again. So in the end, our final pressure at the bottom of the tank, 36 kilopascal. Anybody else get the same thing? Good? All right. So that is another application of the hydrostatic equation if we've got multiple liquids. All right. So now what about this one? 3 liquids, and we've got a lot of different information along the way here. We want to know the specific weight of this third fluid. So we know the specific gravity of the first, the density of the second, and we have a pressure measurement at some depth into the third liquid. So we know that the pressure at a depth of 0.8 meters from the interface is 45 kilopascals. So we know the delta H, and we're going to know the delta P, because what you need to do is you need to find out what's the pressure at the first layer, what's the pressure at the second layer, and so you're going to use this abbreviated version of the hydrostatic equation to find the unit weight of this unknown purple fluid. It's probably grape Kool-Aid. That's my guess, just from the looks at it. We don't know, though. All right, so I'm going to pause the recording, give you some time. So again, what you need to do is find out what's the pressure at these locations. And maybe it's a good idea to label them with numbers just to keep it straight. You know, 1 is at the interface of the air and the yellow one. 2 is the interface of the yellow one and the blue one. 3, and then maybe location 4 is where we've taken this fluid measurement to be 45 kilopascals. I thought it was just at the purple unit.
I didn't think it was.
I got to knock away. Is that 45? Okay, let's go through this step by step. The first thing is, whenever you don't know exactly how to start a problem, you just begin with what you do know. And we know that the pressure of air is 0. If we're working in gauge, the pressure at air is 0. So start where you know something and work towards the unknown. In our case, we're going to be working downward towards the unknown. Okay, so I've got the layers that are numbered here. You maybe numbered it a little bit differently, and that's fine if you did. But I'm saying let's call the interface of the air and that first liquid location 0, where the air touches that first liquid. And so the pressure there is 0. If I want to know the pressure at location 1, which is half a meter deep, then it's going to be the pressure at 0 plus the change. And the change is half a meter of whatever this liquid is. And this liquid, I guess it doesn't matter as long as we got the specific gravity. It's known to be 0.78 times the unit weight of water. And so if we do that, it should be 7651.8 newtons per meter cubed. That's the unit weight of that first layer. So the pressure at 1 will be the pressure at 0 plus the change. So who got 38,026 pascals as we go down through the first layer? Okay, good. So then the principle is, if we want to now find the pressure at location 2, it's additive. It'll be the pressure at location 1 plus the change. So 3,826 pressure at 1 plus the delta P just through that layer. And so the delta P through that layer is going to be 1.55 meters of this liquid, which has a density of 999 kilograms per cubic meter. And to get the unit weight out of that from a density, we multiply the density by gravity, 9.81. All right, so the pressure at 2 is going to be 19,016.2 newtons per meter squared. So it's accumulating the pressure as we go down. Now the last part is we already know the pressure at 3, and we want to say what's the delta in pressure through the place where we're most interested here, because the gamma is unknown. The delta pressure that we're measuring is the pressure change through these two locations. And so the pressure we have to calculate through just the subtraction between the given P3 and the P2 that we've calculated through all the previous steps. And so the delta P between those 2 points is 25,983. And now we rearrange the hydrostatic equation to solve for gamma, because normally we'd say delta P is the unit weight gamma times delta H. But if we rearrange that to solve in terms of gamma, let me zoom out so we can see the sketch at the same time. It's getting kind of small. Maybe 55%. All right, so that tells us the unit weight of that unknown liquid by kind of leveraging the hydrostatic equation to solve for the gamma rather than for the change in pressure. Maybe in a quiz or on a homework assignment, the unknown thing will be to solve for the delta H. You know, like how far down into a liquid do you have to go in order to see a certain pressure? That would be another way of applying the hydrostatic equation. The point is that we can solve for any one of these variables as long as there's some way for us to determine the others. And in this case, when we didn't know the pressure and we didn't know the unit weight, the thing that we could do was we could calculate the pressure at 2 by looking at all of the layers above it. All right, so that's all I have for you today. Let's take one last look at the announcements before you go.
How long will the quizzes be?
Quizzes will be about 15 minutes, maybe 20.
Just curiosity. So that's more like what, 5 questions, a maximum of 2?
Okay, so your next homework assignment is due a week from today. We're going to have the quiz a week from today. And later this afternoon, I'm going to post both the solution to a previous exam and the solution to the homework assignment that you turned in today. So stay tuned to MU Online for great things. See you Tuesday.
Hope I did number 6 correct. That was